my talk is about applications in computer vision using Mathematica 10. I'm using Mathematica 10.2 for this demonstration. I think by now everybody has heard about computer vision. Even if the name is unknown, computer vision is pretty much ubiquitous. You switch on your TV, you see the weather channel, there's some computer vision to remove the green background and put some other map on it. If you're in a car and your car will show you a camera with when you back out, see where if you're standing next to a wall or something, this is again an application. Special effects, Hollywood, etc. So computer vision is very varied in scope. In this talk, I will give an idea of what's available to perform computer vision applications in Mathematica 10. And I will go through 3 applications, one on texture classification, another one on straightening of images, and also on Defmap estimation from stereo vision. So the first one will be very much a classic classic standard application that has been around for a while. Then we'll move on to a more modern task about here touching geometry and computational photography. And then this again about geometry, this time using 2 images. So before I start, whenever I talk about computer vision, I always try to disambiguate quickly the confusion. If you browse through books about computer vision, you can think that computer vision is image processing, it's machine learning, etc. Everybody has their own definition. So as far as we are concerned in Mathematica, all these topics that we categorize as image processing actually would belong as well to computer vision. So the ability you have from Mathematica to acquire live images from remote devices or connected to your computer, the ability to do all types of filtering to your images, what we have in feature detection, where you try to find some little information that you hope later on to aggregate into some meaning of some knowledge of the world that you're hoping to discover. Segmentation, we have, of course, for a while in Mathematica, a whole set of functionality. Registration is a task that is also quite common in many computer vision applications for stitching, for example. So Mathematica offers for a while alignment based on feature and also as well as dense estimation of geometric transformation between pair of images. More recently, we have introduced functionality in computational photography. There will be a talk by my colleague Giulio Alessandrini later this week, I think tomorrow, and you will hear about tone mapping, exposure bracketing, focus bracketing. In painting was there for a while, background removal. So this is ready for you. My talk is about computer vision applications. These applications, they're part of the system, so you don't need to do anything. And finally, I'm sure you all have heard about image identify recently. So this is, I guess, the most bleeding edge in the image recognition and detection. But we have face detection, OCR, and barcode recognition for a while. In the domain of machine learning, this belongs to this talk as well, what Mathematica offers for clustering, nearest neighbor search, classification, prediction. This functionality on a very modern deep convolutional network that is coming up, dimensionality reduction. These topics are very valuable for some applications of computer vision. And Mathematica being this one system, one umbrella system where everything is under the same roof, you will enjoy now development in geometry regions. This can get you out of trouble in a variety of situations. So that being said, let's now, I would like to present what you can do with this system, not so much the features in themselves. The documentation is there for that. So let's move on to the first application. which is about texture classification. What I'm showing here is something that you can think of as a classic. I'm not sure in 2 years anyone will still want to talk about that. But currently, that's a classic way of doing texture classification. And the idea is that you have given an image of a texture. So this will be such typical image. A texture is essentially an image that repeats with a small pattern that repeats itself. So the main idea here is that we are going to engineer features that describe this image, the relationship between neighboring pixels in that image. So in order to do that, we use a tool called the co-occurrence matrix. And if I show you how such metrics look, here I have asked for, essentially I'm looking at, this is like a 2D histogram, and I'm looking at relationship between between neighboring pixels here, left and right. And what this tells me essentially that if I'm all on the diagonal, that means that every pixel has a neighbor that is exactly the same as that same pixel value. If you're around here, you see that's about the case for pixels that are in the mid-tones. But for example, dark pixels or lower tone pixels, you see that they are more widespread. And based on a whole bunch of computation you can do on this matrix, you can actually describe the properties of the pattern in your texture image. So if you just do that co-occurrence matrix on its own, you don't achieve invariance to rotation. So this you can do by just averaging various kernels when you compute the various co-occurrence matrix. And this will essentially be the co-occurrence matrix we'll be working with, and this is invariant to rotation, which is surely for some case of texture classification, you would want to be invariant to rotation. So Aralic has proposed 14 features that can be computed from this matrix. It turns out that in most experiments, out of these 14 features, there's so much correlation between them that it's classic to use a subset of 5. So this is what I'm going to do now. Essentially, those 5s are named homogeneity. They describe the contrast, the correlation, entropy, and local homogeneity. I do not intend to have you, especially after a coffee break, to look into that too much. But once coffee kicks in, maybe for later stuff I would. So essentially, let's just say that after you're done computing this co-occurrence matrix and you compute these 5 features, you have a descriptor of your image. And that is supposed to be a robust description that can be then fed to a classifier. If you are dealing with color images, you can extend that concept by working in the LAB color space and essentially compute the same 5 features, but by looking at pair of channels. So L and A at the same time, compute a matrix, get 5 features, then L and B, then L, and so forth. So if you do that, you can then describe a color image by a vector of 30 values, which I do here for this, not so much of a textured galaxy, I guess. So this is about the theory of these features. And now let's see how they perform when we apply them for a classification task. So I'll be using this data set that was published by nearby colleagues at the UIUC. And I'll be looking at 3 types of bark of woods and 3 types of woods. This data set has more categories than that, but for the purpose of this talk, I focus on these 6 categories. So we have 40 images, 6 types of wood. What you do essentially, before you want to use the function classify, you need to just, on a training set, compute the features and tell the system the class they belong to. So instead of me spending the time computing them, it doesn't take too long, but it's just faster to pre-compute for the purpose of this talk. And then that training set is ready for the function classify. And this function classify essentially takes care of finding for you the type of classifier that is best suited for this data. And here it's a logistic regression. And once you have this classifier, again, I'm going to load, we are going to assess the performance of it. And we need a training set, which I have pre-computed features for already. And now we can see how it performs. So what we can see here is that the overall accuracy is on the test set is 84%. And if I look at the confusion matrix, which tells me that, for example, the first type of bark has been recognized indeed as the first type of bark pretty much all the time, except for three samples. And what you see here is that essentially you have probably something to look at for that first type of wood. Probably you want to either add data to your training set or figure out if there's something else you would like to perform on that. So I'll be now moving on to a completely different topic, which is more talking about computational photography and geometry. So I don't know if you have been to the bottom of the Burj Khalifa in Dubai, but it's pretty high. When you want if you want to yourself to have a look at it, you better almost break your neck or fall backward. And it's the same if you want to take a picture of it. You cannot just have your camera in front of the building and hope to get a full picture of the building. You have to tilt your camera. And by doing this, you capture the entire building, but of course you introduce a lot of distortions. And it may be hard for such a big building, but what you would like is to rectify this image to make it straight again. So that is another example in the urban environment where I guess sometimes you have to hold your camera and try to take a picture above a crowd or something, and later on you want to automatically put it back in straight shape. So that's what we are going to tackle. I may not go into all the details of the application for the Burj Khalifa, but that's the start. So we start first with this toy example of that is very suited for a purpose. It's generated using Mathematica. If I rasterize the 3D graphics, there is actually a perspective transformation that is going on. So I can just show the algorithm I'm going to explain using this toy image. And we want to try to have that cube back straight up. The approach we have here is to try to detect lines. So that's the little object that we are going to work with. So in order to detect lines, we first need to make them conspicuous in the image. Here the human eye is maybe detecting them, but no computer will be able to do that. So once you compute here the gradients, the gradient magnitudes, I have now a very sharp representation of the edges of that shape. And now I can use a function called image lines to detect them. So what image lines is going to do is essentially going to look at all the possible line candidates in these pictures and figure out what is the best fit, what are the lines that best fit the image. So there's various algorithms to that. I will let you look at documentation to understand the details of image lines. But after you are done detecting those lines, here I have specified parameters so that I only get the best lines. And you see that I have indeed detected lines that correspond to this, all the vertical axis as well as the two others, horizontal and as well as depth. So this is good. This is the first part. This is where computer vision folks are now very happy because they have an estimate of lines that hopefully is robust and works well, and now they can derive their additional applied mathematics to combine this information into something of higher level. So the thing we would like to do is to find the intersections of this line. And that will give what is called the vanishing points. And if you know about the position of these vanishing points, you can then derive further information, like you can calibrate your cameras in some cases, or rotate an object in an image. So let's compute line intersections. New in Mathematica 10, there's this function region intersection. So we could actually just give our lines and get a result. But unfortunately, we cannot really do that in this case because I guess region intersection does what it should. So if here I have two lines that are parallel, you see that this is a vertical line, and this is also a vertical line. And the region intersection tells me that they don't intersect. But in computer vision, parallel lines intersect all the time, right? If you take a picture of a road, you see that all the time. So actually, they intersect at the infinity. So we cannot use that framework of region processing right now for this application, even though it can make sense in other times. So instead, we'll just use a classic way of computing intersections. There's two things perhaps I should mention. In the details of it, you may want to use, there are various ways of approaching that. You could use also projective homogeneous coordinates to have perhaps a more robust estimation. But in this case, this works very nicely. And here, what is being done is essentially computing an intersection in Cartesian coordinates and then returning the line parameters as polar coordinates. So returning deviation from the center of the image as well as an angle corresponding to the slope of the line. Another aspect is that many times optimizers will perform better if we help a bit with massaging the data. And in this case, it works better if we express the line with a coordinate system where the center is in the origin is in the center of the image. So I'm just changing my lines so that they're into this new system, and then we can just apply the function that performs an intersection on all the possible lines. So this will be the coordinates where lines intersect. And this is very good. This is very far from the image. The image is perhaps less than 1,000 pixels. So if you have an intersection which is that far back, that's great. You want, that means that you're probably a candidate for a vanishing point. And we have several of them. So, and these are the angles that correspond to the line. So now we can just, since we're interested in putting back buildings up, we can just look at the directions that correspond potentially to the vertical direction. And, I'm sorry. This was actually just getting the directions from the possible vanishing points. You see here, you may be tempted to see three clusters, one for maybe one direction, one for another one, and perhaps one for vertical, horizontal, and depth. Actually, it will be a fallacy to run a clustering algorithm on this data because not every image will exhibit the three levels of perspective. Many images will have two or maybe only one or even zero. So instead, we are doing a very, I guess the smart thing to do here, we just isolate a range where the angle is likely to be, and we select the directions within this range. And after this, you just pretty much try to combine that into a single angle that corresponds to a single vanishing point. So here I just select, I use median, And we can now just rotate that little toy into a stand-up right position. So we can now apply the exact same thing to a real case, a real application. So here I have a Rubik's Cube, and the same, you can see the perspective effect. And in this case, I use contours to, I use as contours a ridge filter that will allow to enhance this dark separation between the faces. And this is exactly the same thing as we just said. We just compute lines, you see them, and then make sure these lines are in a coordinate system that will be robust and compute intersections and figure out the points that are likely to be vanishing points and get directions for them. And voila, you have a straight Rubik's Cube. And I could do the same, of course, for that one of this initial picture I have shown at the beginning. And again, the exact same thing. Perhaps the only thing that varies here is that I look at the gradients to compute my contours that are for line detection, etc. Again, the exact same phenomenon. And you see that this time we may not have achieved that great of a straightening. So making such process automatic on a data set of your entire library of thousands and thousands of images, this will be more challenging than that. There's a kind of scratching the surface here. All right, so I would like to talk about a third application, which is Defmap estimation from stereo. So we have already talked a bit about geometry, and here we're going a little more into it. So here is the scenario. You have two cameras that take pictures of the same scene. So in that pictures, this will be your two cameras, and you see that this point X is a 3D point of the world. And it gets projected on that location in the first image on the left, and this location, X prime, on the image on the right. But if you look at only this point here, and you want to know, but where is it in the right image, then you have an ambiguity, because that point X is actually the projection of all these 3D points here. And these 3D points are at a different location in the right image. So we are going to leverage that information to try to derive an estimation of depth. What we want is to estimate, essentially, when we look at this point X on the image of the left, how deep is the actual point in the scene that is being projected in X. So let's see how we can coerce information from this setup into some information that is valuable. So these are my two images. So this is the left image, and this is the right image. It's a bit staged, as you can see, but it's actually more challenging than it seems. So, all right. So I hope coffee has kicked in now. That's the only equation I have left, I think. The thing we have to find is something called the fundamental matrix. So beside the terminology, it's essentially a matrix 3 by 3 F that allows to map a point in one image to a line in the second image. So if I go back very quickly to this slide here, it will map that matrix F is the matrix that will map this point X to that line, to that blue line here. So if we find this matrix, we will be able to use it to derive information about the depth in our images. So the first thing we need to do is to try to find corresponding points in the left and right images, and then we'll solve an equation for F. So in Mathematica, it's very easy to use image key points to derive such information. And I want to emphasize that even though here key points are being matched based on local descriptors of their appearance, there is no geometric information that is being used when we compute these correspondences. So potentially here we have a lot of false matches, maybe even half of them, just because we do not inject any geometric constraint in that function. So if I look at the result, this is just the first 100 points. And that's pretty much, a lot of them are correct, actually. So it's very good news for the following. So now, how to estimate this fundamental matrix F based on this set of correspondences? Because F is verifying this equation for every point, it is quite easy to recast that problem into a standard linear algebra optimization of the least square type of thing, where you try to find a vector that contains the flat variables of F that explains the best this relationship for all the corresponding points. I don't think I have time to go in details, but that's a bit more complicated than that. If you just do the naive thing, you will have a lot of noise in your result. This is a bit sensitive in terms of numerical way of computing. So in Mathematica, it's actually buried in some context, so I don't need to show the code right now. And this is our result with this matrix F. Even though I have 4 minutes left, we are not done at that moment, because what we have here is a matrix, and we have a set of corresponding points, but we have maybe 400 of them. And what we want is that we have an estimation for every single pixel in the image. So now we are going to see how to go from this very sparse estimation to a dense estimation. And so the first thing we do is what is called image rectification. We are doing this because even though, thanks to the fundamental matrix, I can take any point in the right image and see the line where it is on the left image, it's very expensive if I want to parse lines that are diagonal and so forth. Instead, if I were to move my two image planes so that they are parallel to each other, then the correspondences, I will just need to scan horizontal lines. If I look for the point X on the right image, I know I just need to look along this line to the best match. So allow me, well, I hope you trust me that this is good. And all right, and after we have done this massaging, this is what you get for the rectified image on the left and on the right. And here you see that indeed, when I trace horizontal lines, I get similar alignments. A point here, for example, is at the same place on the same horizontal line. So let me spend a minute explaining how we are going to find the disparity between the 2 points. The idea is that the two images are kind of very close from each other because they are not taken too far apart. So if there's a little patch around the point on the left image, it should not be too different on the right image. So what we are going to do is essentially try to find a good match of the patch on the left image with all the candidates on the line in the right image. So here is a little patch around the nose of that teddy bear. And what the task is pretty much trying to find where is the best match for that nose, and this is the same scale, where is the same position for that nose on that band, that horizontal band. So this is we can just compute the Euclidean distance for every position, and this will be where the disparity will be for that very point. So for that nose here, you see that there is a difference of 4 pixels horizontally between the left image and the right image. So that 4 is what is called disparity. And the higher it is, that means, that's not mine. The higher it is, that means the closer you are from the camera. So the smaller your depth is. Because if you're at the infinity, it doesn't matter that your two cameras are a bit different. If you're very close, that's where you get the most differences. So now, if I want to compute that, actually, that concept explanation I give is too slow to implement. So if I'm willing to give some quality degradation, I can do that much quicker. And that's what I'm going to do now. I compute the disparity using the left image and the right as a reference and vice versa. After that, I can try to reconcile these two estimates. And you see here that when it's black, that means that the two versions are too different to be trusted. So only in this area, actually, I have something good here. And I do a final processing just to essentially find the best estimate based on the disparity from the left and the right. And this is the result you get. If I had more time, I would talk more about what you can do with that. But there's another problem. I have to admit, this is not very, very good. I said that on the edges, you're not supposed to do well with that method, and indeed. But you have too much of areas in the foreground where it's not good enough. So around the teddy bear, it's fine, but that's pretty much the end of the talk for today. I think there will be more coming into that, and I'm on time. Thank you.